This is Radio Ecoshock with your host, Alex Smith.
Extreme wildfires will increase as the planet warms up, the IPCC tells us. New research shows an unexpected twist. These fires are changing chemistry in the upper atmosphere. The impacts can influence global temperatures and damage the ozone shield, protecting us from harmful radiation arriving from space. Peter Bernath is the research professor at the University of Waterloo and principal investigator for the Atmospheric Chemistry Experiment, or ACE. His team uses the Canadian satellite called SciSat and ground measurements. Dr. Bernath got his PhD at MIT and has lectured at universities in Florida and Arizona. He is also an eminent scholar at Old Dominion University in Norfolk, Virginia. From Waterloo, Canada, Peter Bernath, welcome to Radio Ecoshock.
Glad to be here.
Your latest paper title is Wildfire Smoke Destroys Stratospheric Ozone. What was your test fire to reach that conclusion?
So we're making measurements now for many years. In fact, we have 18 years of atmospheric measurements. And so we've been looking in recent years at aerosol spectra, so sulfate aerosols and fire spectra and volcanic eruptions, ash, and so on. And so when we looked at the fire spectra, we were able to get some unique features. And we looked at the Australian fires in 2020, and we noticed these coincident in time changes in ozone and in the composition of the stratosphere. So our mission, this SciSat or ACE, is uniquely able to measure more than 44 molecules in the atmosphere. So we're able to get a very good idea about atmospheric composition, in particular in the stratosphere. And so we noticed all of these unprecedented changes in the stratosphere. That is, things like hydrochloric acid going down, ozone going down, and so on. And they have been induced by smoke. And so this hasn't been seen before. So somehow a new chemistry caused by smoke particles in the stratosphere was observed by us.
When I was reporting on explosions at nuclear reactors in Fukushima, Japan in 2011, we learned radioactivity only becomes global if it reaches beyond the troposphere up to the stratosphere. Is that true of smoke particles as well?
Pretty much. Once the smoke particles get into the stratosphere, the stratospheric circulation spreads it around the globe. The smoke particles in the troposphere, there's a lot of weather and rain, and pretty well things get rained out. Although, of course, they can circulate over a long distance as well. But by and large, once they're in the stratosphere, the tropopause acts as a kind of a barrier, and things then rapidly move around the globe. So, in a couple of weeks, something in the stratosphere will come and go totally around and come back to where it started from.
Peter, please tell us about pyrocumulonimbus clouds. What are they? Can we see them from the ground? And how do they compare to clouds formed, say, by by volcanic eruptions,
So you can certainly see them from the ground. There are these spectacular fires, and in the States they were seen in California this past summer. They had a lot of pyro-CBs there. And so they're nothing more than huge fires, mega fires, and things get so hot that the air gets lofted rapidly up over a very wide area, and the vertical motion is so powerful that it punches into the stratosphere. In fact, it changes the local weather. It's so strong. And these pyro-CBs have just been recognized in the last 10 years or so and studied. So they're a relatively new phenomenon. But certainly, of course, they occurred before then. But their frequency has been increasing. They can certainly be seen from the ground. They're these spectacular pictures that you see where the whole horizon is on fire. And you can see them from airplanes and you can see them from satellites. So they're nothing more than enormous fires. They do have analogies with volcanic eruptions in that they inject soot. Volcanic eruptions inject ash and sulfur dioxide, which ends up making aerosols in the stratosphere. But both cause aerosols to be injected into the stratosphere, and both of them cause the surface to cool by reflecting and scattering sunlight, and they cause the stratosphere to warm because they absorb radiation in the stratosphere, and so they heat the stratosphere slightly. So there are analogies between the two.
You describe in the paper the high-level smoke particles as acidic hydrated soot. What does your new paper tell us about them?
Well, they've never actually been studied by spectroscopy before, so we're really the first group to take spectra of smoke particles in the stratosphere. And it's from the spectrum of these smoke particles that we see water features on the surface of the particles, and we see features associated with carboxylic acids. So we have some indication that these surfaces must be acidic and be hydrated. And these really are the first results for these stratospheric smoke particles that show that. And it seems to be universal. So we have spectra of particles recorded in the northeast United States and Canada from those fires from a few years ago, and they look very similar. So there's some characteristic stratospheric smoke that we've been able to identify.
Did the Australian bushfires of 2019 and 20 affect the size of the ozone hole over Antarctica?
No, there's no connection. It turns out that the effect that we saw was at mid-latitudes in the southern hemisphere, and it never made it to the Antarctic. And in fact, the Antarctic ozone hole that year seems to be unaffected by these fires. Although some of the aerosol particles seem to have gotten down there, but it doesn't seem to have had a big effect on the Antarctic ozone hole.
And you also found wildfire smoke-affected levels of nitrogen dioxide in the atmosphere. Is that the same as the warming gas nitrous oxide? And if so, how does wildfire smoke affect that particular warming gas? Do you know?
Yeah. So nitrous oxide, or laughing gas, is formed on the surface of the Earth from microorganisms, from nitrification and denitrification, and it's inert in the troposphere. But in the stratosphere, it gets dissociated. Well, it actually reacts with oxygen atoms and makes NO, and then that gets oxidized to nitrogen dioxide. So the nitrous oxide, the N2O, is the source for the NO2 in the stratosphere. And in fact, it is one of the major, if you like, natural depleters of ozone. So NO2 reacts with ozone, or NO from NO2 reacts with ozone and causes ozone declines in the stratosphere. But that's a natural effect, if you like. So, the N2O from the microorganisms ends up making the NO2 in the stratosphere. And the N2O is a greenhouse gas in the troposphere, but as I said, it falls apart in the stratosphere and becomes an ozone depleter, if you like, in the stratosphere.
And all these particles are going up into the air. Some of them reflect the sun back into space, and I gather that the short-term effect can be global cooling. Is that correct?
That's correct. So both volcanic eruptions and the fires cool the surface of the Earth. Interestingly, they also warm the stratosphere slightly because, the soot is black, and so it absorbs sunlight. And so in addition to absorbing and scattering the sunlight and cooling the surface, it slightly warms the stratosphere.
Peter Bernath, your research finds the major concern about wildfire changes to the stratosphere is damage to the protective ozone shield. Could you explain the importance of that and in layman's terms how that happens?
Yes, it's quite straightforward because the radiation in the UV is damaging to humans and causes skin cancer, and normally the ozone in the stratosphere blocks that part of the UV radiation. And so if the ozone disappears or declines, more UV radiation gets to the ground, causes more skin cancer, and damages people's health, basically. And so the ozone layer really makes life possible on Earth. Life as we know it can't exist on Earth without the ozone layer. So anything that damages the ozone layer is not good for us, not just humans, but all organisms.
And the Montreal Protocol was aimed at healing holes in the atmospheric ozone, and the hope of the protocol was to restore the ozone layer by the middle of this century. Does your work suggest this could be more difficult or even impossible because extreme fires will continue to damage the ozone?
Well, I don't think it makes it impossible, but it certainly doesn't help. Predicting the future is always a difficult business, and we're not in that game. But certainly this decreases the amount of ozone, and that doesn't help in the recovery of the ozone layer. But the fires themselves, I should point out, the smoke, it's a transient effect. So it lasted for about a year from the Australian fire. So by the end of 2020, the ozone had recovered back to its previous value. And so it's not a permanent effect. And so in that sense, it's not as damaging as the CFCs that the Montreal Protocol is successfully controlling, by the way.
That was illuminating. I appreciate it. One question I didn't ask you that I am interested in is whether the carbon that's released from wildfires is likely to cause some short-term warming, in the sense that how far does it go up into the atmosphere, how long does it stay up there, and is it going to be an impact?
Yeah, well, I can tell you what happens to the carbon.
Okay.
It gets oxidized by OH to make CO2, so it ends up being CO2. A little bit settles back down through the tropopause and ends back on the ground in that form, but it really gets oxidized. So this carboxylic acid that I was talking about, that's, I think, a step in the oxidation of the soot in the stratosphere, because things last a long time in the stratosphere. And so in the end, the carbon gets oxidized and doesn't disappear. It just transforms into carbon dioxide.
So when we talk about global warming, are we talking about something that is happening in the troposphere or something that is happening in the stratosphere?
Well, interestingly, global warming is really on the surface because the temperature of the surface is going up. That's what people care about. However, in the rest of the atmosphere, in particular the upper atmosphere, a little higher in the stratosphere, the mesosphere, and definitely in the thermosphere, so the signature of global warming, if you like, is it gets hotter on the surface and colder higher up. And the reason for that is pretty simple. The main gas is carbon dioxide, and once it gets up high, the atmosphere essentially becomes sort of optically thin, and so the radiation from CO2 that's emitted just goes out to space. And there's more CO2, so therefore more radiation escapes to space, and the upper atmosphere actually cools. And that's a surprise to some people, but that's sort of radiative transfer. But the CO2 on the ground, that's the greenhouse effect, where the CO2 absorbs the radiation and then thermally emits it, and most of that gets blocked because it's optically thick, and it ends up being reflected back on the ground. So like a greenhouse glass pane, the radiation gets trapped in the surface by the CO2. But up high, the CO2, the radiative transfer, the CO2 becomes optically thin. That is, the radiation can escape freely. And so more CO2, more radiation escapes, and the upper atmosphere cools.
So this satellite called SciSat, it was launched in 2003. The expected life was 2 to 5 years. Is it still operating, and is there a plan to replace it if needed?
It's certainly still operating. It's producing data almost as good as ever. Indeed, because of the long time series, it's more valuable than ever because it's monitoring the change in composition of the atmosphere. And of course, as you know, that's what's driving climate change is the changes. And we see that, and we measure that, and we measure all the Montreal Protocol gases, almost all of them. And so we see that the Montreal Protocol is working, for example. And with respect to replacing the satellite, there's always talk about it, but no action.
Peter, your work's not just earthbound. You also study molecular astronomy. What is that, and what are scientists trying to find out?
Well, essentially you can't, except for our own solar system, you can't actually sample things outside our solar system. And so if you want to study the composition of stars and now exoplanets, you have to do it by spectroscopy, the same kind of remote sensing that we're using with SciSat. And the astronomers need some help from laboratory spectroscopy to understand what they're looking at. And so we have NASA funding, for example, to look at molecules that are found in hot exoplanets. So exoplanets are planets around other stars, rather than in our own sun. And so we make laboratory measurements and analyze the data to predict and help the astronomers model what they see in exoplanets. And there's now thousands of exoplanets. They're typically hot, and those are the ones that we're providing data for. But of course, the long-term goal is to find cooler Earth-like exoplanets and get the composition of their atmosphere. And again, that's all done by spectroscopy, the same kind of measurements that we're making in the Earthsat.
I see a lot of this coming out of Einstein's work on what light really is.
Indeed.
From the University of Waterloo and the Atmospheric Chemistry Experiment Lab, we've been speaking with Professor Peter Bernath. You can find links to the new science we just talked about in my show blog at ecoshock.org. Peter, thank you for sharing your time with us.
Thank you.
I'm Alex Smith for Radio Ecoshock.
You're listening to Ecoshock Radio for the world.
I'm Alex Smith. Get it all at our website, ecoshock.org.